Hello again, and welcome to our next module on clean architecture. I'm Matthew Renzi with Pluralsight, and in this module we'll learn about testable architecture. As an overview of this module, first we'll learn about test-driven development and how it drives the design of an architecture that's testable, reliable, and maintainable. Next, we'll learn about the test automation pyramid and the various types of tests that we can create for our architecture. Then we'll discuss the pros and cons of implementing a testable architecture. Finally, we'll see a demo of our testable architecture in action. So let's get started. Let's start with what we already know, the current state of testing in the software industry. Unfortunately, despite great advances in both testing practices and technology to enable software testing, many software developers still do very little automated testing of their code. And when they do, it's relatively ineffective or highly inefficient. There are numerous reasons given for why developers don't create high-quality, automated tests for their code. These reasons include not having enough time to create tests, it's not my job to test software, testing is for testers, not developers, and it's too hard to create good tests because our architecture makes testing difficult. While there are compelling counterarguments to each of these claims and more, we're going to be focusing on the last of these three arguments during this course. We're going to show how clean architecture actually makes testing easier, not harder. In addition, how test-driven development drives the design of a clean architecture. These two forces work side by side to create a feedback loop that feeds into one another. Test-driven development is a software practice where we create a failing test first before we write any production code and use this test to drive the design of the architecture. We refer to this three-step process of test-driven development as red, green, and refactor. First, we start by creating a failing test for the simplest piece of functionality we need to create. This is the red step of the TDD process. Next, we implement just enough production code to get that failing test to pass. This is the green step of the process. Then, we refactor our existing code, that is, we improve both the test and production code to keep the quality high. This is the refactor step in the process. We repeat this cycle for each piece of functionality in order of increasing complexity in each method and class until the entire feature is complete. By using the test-driven development practice, we are creating a comprehensive suite of tests that covers all code paths of importance in our application. In addition, by using TDD, the design of each of these classes and methods is being driven by the testing process. This means that all classes and methods will be easily testable by default, since the tests are driving the design. In addition, this coincidentally makes our classes and methods more maintainable because of an interesting parallel in the physics of cohesion and coupling with both testability and maintainability. Essentially, by creating testable code, we are coincidentally creating more maintainable code. More importantly, this comprehensive suite of tests eliminates fear. Fear that making changes to our code will cause regression errors in our software. If we can eliminate the fear of change in our architecture, we are more likely to embrace change and keep our architecture clean. While I'm personally a very strong advocate of test-driven development and would really like to cover it here extensively, unfortunately, we'll have to defer a more in-depth discussion of TDD to another course. What's important to note for this course is that test-driven development is a key component to creating a clean and testable architecture. There are a variety of types of tests that exist in the world of software testing. Some tests are based on what they are testing. For example, unit tests, integration tests, component tests, service tests, and coded UI tests. Some are based on why they are being tested. For example, functional tests, acceptance tests, smoke tests, and exploratory testing. Still, others are based on how they are being tested. For example, automated tests, semi-automated tests, and manual tests. While we don't have time to cover all the various types of tests that can be applied to our software architecture, we will, however, cover a subset of the most common of these types of tests and how our clean architecture makes them easier rather than harder to create and maintain. In the book Succeeding with Agile, Mike Cohen describes a concept he referred to as the test automation pyramid. The test automation pyramid identifies four types of tests. First, we have unit tests, which are automated tests that verify the functionality of an individual unit of code in isolation. Second, we have service tests, which are automated tests that verify the functionality of a set of classes and methods that provide a service to the users. Third, we have coded UI tests, which are automated tests that verify the functionality of the full application from the user interface down to the database. Finally, we have manual tests, which are tests performed by a human that verify the functionality of the full application as well. The test automation pyramid captures the essence that each type of test becomes more costly the further up the pyramid we go. As a result, we want to have a large number of low-cost tests and a small number of high-cost tests. For example, unit tests are relatively quick and easy to create, run extremely fast, rarely fail due to false positives, and are relatively inexpensive to maintain. So they are much less costly than the other types of tests. However, coded UI tests are much more difficult and time-consuming to create. They also run much slower, they're more brittle, relatively unreliable, and relatively more difficult to maintain. So they are relatively more costly than other types of tests lower on the pyramid. Given this, we want to maximize the return on investment from our testing efforts by creating the right balance of each type of test relative to the cost of the test and the benefit that the test will provide. So, we should anticipate creating lots of small, low-cost unit tests, some medium-cost service tests, a few high-cost coded UI tests, and very few repetitive manual tests. Doing so, in theory, gives us the most bang for the buck for our testing efforts. One final type of test that I'd like to discuss is a type of test called an acceptance test. Acceptance tests verify the functionality of the application like the other tests do. However, the main difference is that they are typically written in the language of the business and used as the criteria by the product owners and product stakeholders to determine when a certain feature is considered complete and functioning as expected. These tests are often done either as manual tests or as coded UI tests. However, using manual tests and coded UI tests for acceptance testing is problematic for the various reasons we discussed earlier. So, one place where clean architecture really helps us make testing easier and get the most value out of our acceptance testing is by allowing us to replace high-cost manual and coded UI acceptance tests with automated service-level acceptance tests. This is possible with clean architecture because all of our application and domain logic can be tested in isolation. To do so, first, we eliminate the user interface from our acceptance tests. We do this by having our acceptance tests work directly with the commands and queries in our application layer. Next, we eliminate the database from our acceptance tests as well. We do this by mocking out the real database with a fake in-memory database instead. Then, we mock out the operating system and any external dependencies in the infrastructure layer. We do this by replacing the dependencies with fake test doubles called mocks that act as surrogates for the real dependencies. We also do the same for our cross-cutting concerns. Acceptance criteria should be written in the language of the business to describe business functionality that the application needs to provide. They should focus on what is essential to the business and not implementation details. Thus, implementation details like presentation, databases, third-party dependencies, etc. should all be irrelevant to these acceptance criteria. In addition, because we've kept our presentation, persistence, and infrastructure projects thin, that is, they contain minimal logic and no application or domain logic, eliminating them from our acceptance test should pose little risk from the standpoint of verifying business functionality. However, there can be exceptions. For example, verifying non-functional requirements, security requirements, or auditing requirements, but we can handle verifying these types of non-functional requirements in other ways. With this style of acceptance testing, our acceptance tests are focused on what is essential in our application, that is, the business domain and the use cases in the application layer, not the implementation details like databases, operating systems, third-party dependencies, or cross-cutting concerns. Doing this allows us to minimize the number of coded UI tests in our application. So, rather than using coded UI tests for acceptance testing, we can instead reserve them for what are called smoke tests. Smoke tests are a very small number of simple full system tests that just verify that the application actually runs and nothing more when all the pieces are assembled at runtime. This reduces the cost of creating and maintaining a large number of these costly and complex coded UI acceptance tests and reduces the likelihood of false positives, which degrades our confidence in our comprehensive suite of tests. In addition, this also allows us to minimize the number of manual acceptance tests as well. Thus, we reduce our manual testing costs and free up our testers to do much more valuable and rewarding work, like exploratory testing and ensuring a high-quality user experience for our end users. We'll see a brief demo of how these service-level acceptance tests are implemented in our demo application shortly. So why would we want to use a testable architecture? First, by applying these testable architecture practices, we make our code easier to test, and if our code is easy to test, we'll be more likely to create and maintain these tests. We want our architecture to encourage developers to write tests and to practice test-driven development. Second, creating testable architecture improves the design of our architecture. This is because the physics of cohesion and coupling of testable code parallels that of maintainable code. So, by virtue of adopting test-driven development and creating a testable architecture, we're actually creating a more maintainable architecture as a result. Third, by creating a comprehensive suite of tests for our architecture, we eliminate fear. By eliminating the fear that changes to our code will break the code, we're much more likely to embrace change, continuously refactor our code to improve it, and keep our architecture clean. So why would we not want to create testable architecture? Honestly, there are very few reasons I can think of to not want to create testable architecture. In fact, testability is probably one of the biggest selling points in my opinion for adopting clean architecture practices. However, for the sake of counterargument, I'll do my best to articulate a few cases where you might not want to create a testable architecture. First, there's an initial higher upfront cost to using test-driven development and creating testable architecture. So, for a very small project or for disposable software projects, for example a simple throwaway console application with clear and stable requirements, it might be more cost-effective to just build the tool and test its narrow functionality by hand. Second, test-driven development requires practice and discipline. It's not something you just learn in a day, and it takes quite a bit of practice to become highly proficient with TDD. In addition, it requires a lot of discipline to keep yourself from falling back into your old coding habits. Third, testable architecture practices usually require buy-in from the whole team. If the whole team isn't creating testable code, running all of the tests, and maintaining these tests, then the test in the testable code will eventually decay and become obsolete. So while I personally think it's very unfortunate, some teams simply just are not interested in creating automated tests or writing testable code. So now let's see our testable architecture in action in our demo application. Now we'll see our testable architecture in action in our demo application. This entire demo application was created using test-driven development. That is, I started each feature with a failing unit test, then I created just enough production code to get the test to pass, then I refactored the code to improve its quality. Finally, I repeated this process until each feature was complete. While I would prefer to show you a demo of me creating the application using the TDD process, unfortunately that would take much more time than we have available. So we'll have to defer that demonstration to another course. However, I would like to show you just a few unit tests in the domain and application layer and a service level acceptance test for this demo application. All of these tests will involve the functionality to create a new sale that we've already seen in previous demos. During this demo, we're going to be using a few tools that you might be unfamiliar with. For example, NUnit, Mock, AutoMock, and SpecFlow. However, I'll do my best to explain what they do as we proceed through the demo. If you're having difficulty understanding what the tools are doing or how they work, no worries. This is mostly to get you interested in learning more about testing software this way, in the hopes that you might invest time learning more about testable architecture in the future. Let's start with something simple. Let's begin by looking at the unit tests in the sale test class. This test class contains all of the unit tests for the domain logic of the sale class in the domain project. The class begins with a test fixture attribute. This attribute tells NUnit, which is our unit test framework, that this class contains tests that should be run as part of our suite of tests. Inside this class, we have 4 private fields. 1 for our sales class, which is our subject under test, and 3 more for a customer, employee, and a product, which are entities we will be using while we test the sales class's functionality. Below this, we have some private constant and private static fields to hold values we'll be using for setup and verification. Next, we have the setup method of this test class. This method is marked with the setup attribute. This attribute tells NUnit that this method should be called before each unit test is run to set up the necessary preconditions for the test. In this method, we create our 3 dependent entities, that is, customer, employee, and product, and then assign them to the private fields we saw above. Finally, we create a new sale class, which as I mentioned before is our subject under test, and assign it to the sale variable above as well. Now let's take a look at the actual unit tests contained in this test class. The first test method is called testSetAndGetID. This unit test will simply test the property getter and setter for the ID property. We mark this test method with the test attribute, which tells NUnit to run this method as a unit test. Inside this method, we set the ID of our sale entity to the value contained in the private constant integer field called ID that we saw above. Then, we assert that the value now returned from the sales ID property should match the value property we are expecting. If these 2 values match, the test passes. If not, the test fails. The remaining unit tests for property getters and setters looks pretty much the same, so we'll just skip over them. These are relatively low value unit tests since there's minimal logic being covered in these tests. However, they are created as a result of using the test-driven development process and are necessary to maintain a comprehensive suite of tests for our domain logic. The more interesting unit tests in this class are the 2 unit tests that verify the logic to calculate the total price of the sale. The first of these 2 tests sets the unit price and verifies the total sales price is recomputed to the correct value. First, we set the sales quantity property to the quantity of products sold from the quantity constant we saw at the top of the file. Next, we set the unit price to a simple arbitrary value like 1.23. Finally, we assert that the value returned from the total price property matches the expected value of 1.23. The final test in this test class also tests the total sale price logic, but does so by setting the quantity rather than the unit price and verifying the correct sale price is returned. Now we'll look at a much more complex example. We'll look at the unit test contained in the createSale command test class. This test class provides unit tests for the production createSale command class, the same class we looked at during 2 of our previous demos. This class creates a new sale, saves the sale to the database, and notifies the inventory service that a sale has occurred. This type of test would generally be extremely difficult to test in isolation if we're using traditional architecture, patterns, practices, and principles. However, as we'll see shortly, it is completely testable in isolation in our clean architecture. Once again, this test class is marked with the test fixture attribute to indicate to NUnit that it contains tests that need to be run. The class begins with 4 private fields, a field called command, which holds the createSale command that will be used for testing, that is, our subject under test. A field called mocker of type AutoMocker, which is a tool that makes mocking dependencies easier, that is, it will make it easier to swap out interfaces with fake test doubles. A field called createSaleModel, which will hold the data for creating a new sale, and a field called sale, which will act as a placeholder for the sale being created. Next, the class contains a series of private constants and static fields to hold values used during our testing process. The setup method for this class is marked with the NUnit setup attribute like we saw before to tell NUnit to run this method before executing each test. Within this setup method, we create a new customer, a new employee, and a new product. Then we create a create sale model and assign it to our model variable. We create a sale and assign it to our sale variable. We construct a new automocker and assign it to our mocker variable. Then we use our newly created automocker to get a mock iDate service. This creates a fake test double for our date service that adheres to the iDate service interface. Once we have our fake date service test double, we set up its getDate method and tell it to always return the test date value that we created at the top of the class. This way, anytime our sales controller class calls getDate, it will always get the same date no matter what day, month, or year we run this test. Next, we set up fake DB sets for our customers, employees, products, and sales repositories. The details for how this is done are in methods at the bottom of this test class. We'll take a look at these methods later. For now, all you need to know is that these methods are creating a simple in-memory repository for each type of entity so that we can work with these test entities without needing an actual database to store them. The first three methods also add a single customer, employee, and product entity to these in-memory repositories. Then we use AutoMock to create a new mock sale factory. This will create a fake test double for our sale factory class. Doing so allows us to decouple the low-level logic for how to create a sale domain entity from the high-level application logic for how to create a sale, save it to the database, and notify the inventory system. In addition, by doing so, we're adding a seam in our code that will allow us to inject a sale entity, which makes testing easier because we don't have to create a new sale class inside of our create sale command. Finally, we use AutoMocker to create a new create sale command, and we assign it to our command variable. Now let's take a look at the actual unit tests in this test class. First, we'll start with the test execute should add sale to the database test. Once again, this method is marked with a test attribute, which tells NUnit that this method is a test method to be run. We've already done all of the necessary setup for this test in the setup method we saw earlier, so we don't need to do any additional setup before running this test. Next, we execute the create sale command and pass in our create sale model as an argument. Then we use AutoMocker to verify that the add method of the mock sale repository has been called exactly once. If that is the case, the test will pass. If not, the test will fail. Next, let's take a look at the test to verify the execute method should save changes to the database. Once again, all of the setup for this test was taken care of in the common setup method, so we just execute the command and then use AutoMocker to verify that the save method on the mock database service has been called exactly one time. Then we'll look at the test that verifies that the inventory system should be notified that a sale has been created. Once more, the setup of this test has been taken care of in the setup method. So we call the execute method, then we verify that the notify sale occurred method on the mock inventory service has been called exactly one time with the expected product ID and the expected quantity of products sold. Finally, at the bottom of this class, we have two private methods to set up the mock database repositories. These methods are a bit complex, so I won't go into too much detail. However, in general, they create a new generic .NET list typed to a specific type of entity using an extension method that I created and stored in the common project. Then, they return that list of entities when the specified property corresponding to those entities is called on the mock database service. So the create sale command class will think that it's talking to a real table of entities in a database, when in fact it's just talking to an in-memory list of those entities instead. I should probably note that typically these two methods would eventually end up being refactored out of this test class into a shared location once multiple test classes needed this functionality. Finally, let's take a brief look at the service level acceptance test for our demo application. To go in depth would require more time than we have during this demo, but I want to show you the basics of how we're able to isolate our application and domain logic from its external dependencies and create tests in the language of the business to verify the correct business functionality of the application. This part of the demo uses a tool called SpecFlow. SpecFlow allows us to describe a feature and a set of corresponding tests to verify the functionality of that feature, all using the language of the business. Behind the scenes, SpecFlow parses the English text and matches it to C# code. So we can create, run, and verify a set of business specifications that testers, business analysts, and product stakeholders can read and understand. Once again, we'll be focusing on the functionality to create a sale. We'll start with the create a sale feature file. This file describes the create a sale feature in the language of the business. It states, as a salesperson, I want to create a sale to record a sales transaction. The scenario being tested is the most basic test for creating a sale, which we refer to as the happy path in software testing. This happy path test, like the feature it belongs to, is also titled create a sale. The test reads, given the following sale info, followed by a table with one row of sales data, when I create a sale, then the following sales record should be recorded, followed by a table of the expected sales record. And the following sale occurred notification should be sent to the inventory system, followed by a table of the data to be sent to the inventory system. This test describes the process for creating a sale from a high-level perspective in English and in the language of the business. It discusses customers, employees, products, sales, records, and notifications. However, there's no mention of low-level technical implementation details like user interface components, database tables, or external web APIs. The underlying code that actually runs this test is contained in a SpecFlow step file titled Create a Sale Steps. This is a plain old C# class file that contains executable code. SpecFlow automatically handles mapping the English test steps in the feature file that we just saw to methods in this file. While I won't go into the details of this code or how SpecFlow works, let's just scan through the key points. In the constructor of this class, we inject a class called AppContext. This class represents the entire application held in isolation. It contains fake test doubles for the database, the inventory system, and all operating system dependencies. We mock out all these dependencies in the same way we did in the previous unit test demo we saw. However, now we're doing it for all the key external dependencies in the application. It's essentially like we're putting the entire application and domain layers in a bubble so that they are running in memory but completely isolated from the outside world. The first method in this class is tagged with the given attribute. The text string in the attribute matches the English text for the test step in the feature file we saw earlier. The method itself takes a table of data which is populated with the table of data we saw in the feature file. This method then performs the logic to set up external dependencies like the date service and create the input that the user would be inputting into the system. The next method handles the step described as when I create a sale. This method creates the create a sale command and passes it the create sale model, which represents the user input that was created in the previous step. The next method handles the step described as then the following sales record should be recorded. This uses the table of expected data from the feature file to verify that the correct information was saved to the database. Finally, we verify the last step, that is, then the following sale occurred notification should be sent to the inventory system. This method uses the table of expected values to verify that the inventory system was notified with the appropriate data. While I would really like to spend more time on the topics of testable architecture, test-driven development, and acceptance testing using behavior-driven design, unfortunately, we need to move on to our final topic. While brief, this module was necessary to demonstrate how clean architecture makes testing easier and how effectively testing your code drives the design of good, clean architecture. In addition, I really want to spark the idea of why testable architecture, test-driven development, and acceptance testing are so important so that you'll have the motivation to seek out additional information and training on these topics. Finally, I strongly encourage you to spend time with the downloadable demo project to inspect all of the unit tests and acceptance tests in this project. The demo project has great examples of effective and maintainable unit tests, acceptance tests, and testable classes, all created using test-driven development and behavior-driven design practices. In this module, first, we learned about test-driven development and how it drives the design of an architecture that's testable, reliable, and maintainable. Next, we learned about the test automation pyramid and the various types of tests that we can create for our architecture. Then, we discussed the pros and cons of implementing a testable architecture. Finally, we saw a demo of our testable architecture in action. In the next module, we'll learn about how to evolve our architecture and wrap things up for the course.